Hi, I'm Connor, and today my partner Dylan and I are going to present a novel method to reduce the emissions and fossil fuel usage in a chemical pulping plant through electrolytic hydrogen and oxygen production. Currently, pulp plants are able to generate power for sale in the local grid using recycled steam energy. The production of white liquor in the lime cycle produces large amounts of carbon dioxide as a byproduct. Lime reburning requires temperatures in excess of 900 degrees Celsius, powered primarily by fuel oil or natural gas. The objective of this project is to determine the potential for running an industrial electrolysis plant from the excess heat created in steam processes, then burning the resulting hydrogen in the lime kiln to reduce the required fossil fuel. This includes recycling the oxygen byproduct in the bleaching process. The goal of this project is to validate that this electrolytic application would be both financially and environmentally feasible for current and future kraft pulp plants. The primary goal of inducing an electrolytic process in the mill is to produce hydrogen gas, which can then be burnt in a modified lime kiln along with typical fossil fuels. The combustion of hydrogen produces a large amount of heat per kilogram. However, since hydrogen gas combusts easily and is very light, it is tricky to transport and burn efficiently. These concerns are easily addressed when the hydrogen is immediately used on site. Although natural gas produces less carbon dioxide than fuel oil per watt, the cost of extraction and transportation must be accounted for. Due to the leakage of methane, natural gas power plants are actually often worse than those burning coal. Replacing the fuel oil, or even some of it, will greatly decrease the carbon footprint of this process. For every gallon of fuel oil, 11.27 kilograms of carbon dioxide is produced. With plants using upwards of 150 tons per day of fuel oil, a single lime kiln can produce upwards of 446,000 kilograms of CO2 every day. Electrolysis is the process of separating hydrogen and oxygen in water by use of a DC current. On the right is a diagram of an alkaline electrolysis cell, and on the left is an image of a real-life cell in operation. Electrolysis is a carbon-neutral method of storing energy by producing combustible hydrogen gas. In fossil fuels, pollutants are related to carbon-containing compounds released during the burn, but burning pure hydrogen produces no carbon. Electrolyzing water also produces oxygen, which can be used in environmentally friendly bleaching processes. In this case study, the oxygen produced as an electrolysis byproduct is sufficient to meet the bleaching needs of the studied plant. To demonstrate the potential for using electrolysis to produce lime kiln fuel, an existing mill was modeled. The selected model was developed for the paper The Impact of Lignin Removal on the Dimensioning of Eucalyptus Pulp Mills by Hamaguchi, Vakkilainen, and Ryder. This model was used in the original paper the video is based on. In the shown case, fuel oil was replaced with the maximum amount of hydrogen possible to produce the plant. Since hydrogen has a very high energy density, 119 tons of fuel oil can be replaced with only 38 tons of hydrogen gas. The selected mill produces 1,500,000 air-dried tons of eucalyptus pulp annually, or 4,286 air-dried tons per day, with 350 operating days per year. Oxygen requirements for delignification and bleaching are 86 tons per day. The plant uses 164 tons of fuel oil daily to meet a lime kiln heat demand of 72 megawatts. The total electricity generation is 165 megawatts, with 89 megawatts consumed by the mill. The results of the case studies are indicative of the potential gains of using an electrolytic process. As Case B uses the maximum amount of electricity possible, Case B uses a little more than triple the electricity of Case A, which only produces enough oxygen to meet the demands of the plant. Hydrogen production increases by more than 25 tons per day, and oxygen by over 200. Much more feed water and cooling water are required. Inlet, outlet, and reaction temperatures of the water are held constant for both cases. The amount of electricity for sale in Case A is 72% what it would be without electrolysis. Oil requirements decrease by 20% in Case A and a whopping 73% in Case B. One pound of fuel oil with a standard 50% excess air produces 3.16 pounds of carbon dioxide. In Case B, 119 metric tons of fuel oil would be saved per day. This fuel oil would instead be replaced with 38 tons of hydrogen gas. That's 131,000 metric tons of carbon dioxide per year, which, according to the California Air Resources Board, is equivalent to 28,300 passenger cars not being driven. There are three key factors to consider when evaluating the effectiveness of implementing electrolysis into a kraft pulp mill: electricity price, possibility to sell electricity, and fossil fuel price. This excludes the invisible value of reducing net greenhouse gas emissions, which should always be considered by responsible plant owners when evaluating capital work. Note that this economic evaluation does not consider the capital cost of installing electrolysis in the plant either. It is assumed that the method would not be financially viable for installation in a plant with existing oxygen production means. Implementation of hydrogen storage is economically desirable in locations where barrels of oil are prohibitively expensive and in places where electricity resale prices are low. Here are the graphs for profitability versus non-profitability for case. The following graphs indicate whether case A or B would be profitable to implement. According to ChooseEnergy.com, the following prices are highest and lowest in the US in November 2018. Note that these prices are in cents per kilowatt hour, which is equivalent to $10 per megawatt hour. Combining this with oil pricing information from Business Insider, it is possible to find where it would be profitable to implement the process right now. Arkansas is considered the lowest possible rate at $90.1 US per megawatt hour. Oil currently costs $60 US per barrel. Observing the best case scenario shows that the process is currently unfeasible in the United States. Though not directly more profitable than selling electricity to the grid, there are many benefits and circumstances where this application is relevant. Calculations performed for this study did not consider savings in purchasing oxygen. Furthermore, if a new plant was built with excess oxygen production in mind, more processes could be designed around it. There is also the potential to upgrade it to be used as the more effective ozone. This could potentially offset the cost. In summary, the integration of electrolysis can be both financially and environmentally feasible. Alkaline electrolysis was examined based on producing sufficient oxygen for bleaching and on using all the electricity available, resulting in a 20% and a 73% drop in fuel requirements at the selected plant. The environmental impact of implementing the system at the given eucalyptus mill would be the equivalent of removing 131,000 metric tons of CO2 from the air every year. Using electrolysis may be financially beneficial in the future as oil prices rise and electricity prices drop. The system is only beneficial if and when the fuel price oil is high and electricity can only be sold cheaply.